Welcome everyone to the next lesson in this series, and in this video we will look at maximum transmission unit for Kubernetes networking. Now this one tends to be a common pitfall, and the reason I decided to create this video is because I've been on several incident calls where the issue was a mismatch in MTUs. Now in Kubernetes clusters you have to think about MTUs at different levels of the network. So to start off, we have MTU at the pod interface level, then MTU for the host interface, and MTU for your end-to-end network. You have to be deliberate about what these values are by considering the nature of your workloads, their networking requirements, as well as the capabilities of your networking hardware and the MTUs configured in your wider network. Now, the MTU is basically the maximum transmission unit up to layer 3. So that includes your IP headers, your TCP UDP headers, and the payload, the data that you're transmitting. Now, there's also something called the MSS, the maximum segment size. And in a TCP session, the client and the server negotiate the maximum segment size for that session based on their MTUs. Now, although this diagram indicates an MTU of 1500, in modern data centers which support jumbo frames, the MTU is typically 9000 bytes. Now, when you subtract the headers, you get the maximum segment size. So if your MTU is 1500, your MSS tends to be 1460. And if your MTU is 9000 bytes, your MSS tends to be 8960. Okay. So next in this lab, let's look at how the MTU impacts the behavior of your Kubernetes clusters. Let's get started. Okay, so this lab can be found in folder 1818-MTU. I've already gone ahead and deployed the lab in my environment, and this is the topology of the lab. This is very similar to the topology that we had for the overlay networks lab. And the reason is we want pods in different worker nodes to traverse or get routed by the network to demonstrate some of these MTU concepts. Okay. So once the lab is deployed, you can do a kubectl get nodes, and this is a 4-node Kubernetes cluster. And if you do a kubectl get pods dash or wide, we have a couple of pods, a netshoot client and a netshoot server. The client is deployed in worker 1 and the server in worker 3, and these two worker nodes are in different networking subnets. And what that means is when the client has to communicate with the server, it has to traverse and get routed by the upstream network. All right, so first I'm going to do a kubectl exec netshoot and look at the interface of the pod, the EAT0 interface. And this interface has an MTU of 1450. And this is Calico's default configuration. And the reason it's 1450 is because Calico takes 1500 and then subtracts 50 for the overhead in the VXLAN tunneling protocol. So VXLAN needs 50 bytes. So 1500 minus 50 is 1450. Next, let's look at the host interface. So in this example, worker 1, ETH1 has an MTU of 9000, right? So just off the bat, there is a mismatch in the MTU configuration between the host and the pod interface. This is typically not an issue provided that the MTU in the pod interface is lower than the MTU configured in the host. However, we'll look at why there is this mismatch and how this can be rectified. All right, so next what I'm going to do is I'm going to obtain the IP address of the netshoot server, and then we are going to initiate a ping from the client to the netshoot server, and that ping is successful, right? So no issues there. And as you can see, this ping was sending 64 bytes. So 64 bytes, each packet is 64 bytes from the client to the server, and no issues there. Now, if I increase the size of the ping and also put a flag so that these packets don't get fragmented, what we're going to see is that this ping fails because the packet is too large. And that's because the pod MTU is 1450 and I'm sending a packet that is 8900, which is too large for the pod interface. And this packet cannot be fragmented into smaller packets as well. As a result, it gets dropped by the pod interface. So here we have a diagram depicting that. I'm sending packets which are 8900, and my pod interface is 1450. As a result, these packets get dropped. Now, what we're going to do is in Calico, there is a installation resource. If you do a kubectl get installation dash o YAML, and this is a resource that we feed into the Calico operator during install. And in this installation resource, I have not defined the MTU for my pod network. So what we're going to do is we're going to patch the configuration and define an MTU for the pod network. And now you can see that the MTU is 8950. And the reason it's 8950 is because my host interface is 9000. I subtract 50 for the VXLAN overhead, and then I end up with 8950. So ideally, you want to specify the MTU value of your cluster before you spin up the pod network. Now, with an MTU defined, I am going to delete the Netshoot client and server pods. And the reason is these pods were already spun up with a certain MTU 1450 for their pod interface. I'm going to delete the pods and provision them once more. They will then pick up the new MTU configuration for the pod network. All right, so once deleted, I'm going to reapply the manifest for the client and the server. You can find it in the tools folder in the folder for this lab. And once those pods are up and running, what I can do is another IP link show, and we can see that the MTU this time around for the Netshoot client is 8950, and it'll be the same for the Netshoot server as well. Okay, so these pods have now come up with the new MTU values for the pod network. And let me once more obtain the IP address of the Netshoot server. And if I do a ping from the client with a packet size of 8900, this time those pings are successful, right? So you got to make sure that you specify the MTU values based on the MTU values that you've configured for your host interface. And also make sure that the MTU values configured in the host interface align with the values of the rest of your network. Okay, so next we're going to look at the MTU in the top of rack switch. So if I go back to my lab and exec into the Arista CEOS image, let me do an enable and a show IP interface brief. The MTU for VLAN 10 and 20 is 9000. The MTU for the management interface is 1500. You can ignore that for this lab. And now I am going to run a command, a curl basically, from worker 3, which is in VLAN 20, to the control node, basically the Kube API in the control node, right? And this basically simulates how kubelet connects with the Kubernetes API. Let me first exit from the Arista CEO's image, and let's just run that curl again. And as you can see, the curl is successful, right? So I'm essentially from worker 3, I'm doing a curl to the Kube API in the control node, and that packet obviously has to traverse the top of rack switch, the router in this case, and arrive at the control node. Now, as a test, what we're going to do next is change the MTU for VLAN 20, right? So I'm going to run these commands and change the MTU for VLAN 20. Once done, you can exit from the top of rack switch. Sorry, before that, once you've done the change, let's go into the switch one more time. If you do a show IP interface brief, the MTU for VLAN 20 should now be 1500 after you made that change. So let's now try doing that curl. And as you can see, it's gonna time out. Okay, so essentially, if you look at VLAN 20, the MTU is 1500. So now there is a discrepancy in our end-to-end MTU path. And when this node does a curl to the control node, that curl is now timing out. We can see an SSL timeout. So this is a telltale sign of a MTU mismatch. In most cases, when I've looked at MTU issues, it manifests itself as an SSL timeout. Or if it's something like a database, you could have a DB call getting timed out. So here's that timeout one more time, okay? And the tricky thing about this timeout is if you look at a verbose output, you are going to see a successful TCP handshake. And what this essentially means is that you have end-to-end network connectivity, but the TLS handshake is not able to complete because the certificate exchange is going to send large packets which are going to get dropped by the network, whereas the TCP exchange only sends small packets that can still transit through the network, right? So although you have end-to-end connectivity as depicted by this connected status between the server and the client, it's not able to complete the TCP handshake. Now, the reason the packet gets dropped is because a lot of modern networking stacks set the do not fragment bit to one, as in to inform or instruct upstream network devices not to fragment the packet, because fragmentation is expensive. When you fragment packets, you have to process all the packets individually. If a fragmented packet gets dropped, you have to retransmit the entire packet. And fragmentation could also have security concerns. So a lot of modern applications rely on not fragmenting the packet, and as a result, when the network receives a packet that is larger than its MTU, it's going to drop that packet. Now, there's something known as the Path MTU Discovery Protocol. So, a network device such as our top of rack switch, when it drops the packet, it sends an ICMP message back to the sender, informing the sender that the packet needs to be fragmented and to reduce the maximum segment size for that TCP communication session. However, in production networks, you cannot rely on path MTU discovery because the ICMP packets tend to get dropped by the network. You could have network firewalls in the intermediary path that drop ICMP messages, or given how your network is architected, the ICMP message may never reach the sender. So, this is not something you could absolutely rely on, although it's good to bear in mind that there is such a protocol that works for TCP sessions, and senders have the ability to adjust the MSS of a session based on path MTU discovery, and we will look at how that works next. Okay, so for this next section, we're going to open 3 terminal sessions. So I've opened 3 terminal sessions, and in the new terminals, you can connect to your EC2 instance, and if you deploy this in a home lab, make sure you just SSH into the lab instance. I'm going to CD into the lab folder and do the same for the other terminal instance here as well. All right, so I have now opened 3 terminal instances here. And what we are going to do is in the first terminal instance, we are going to run a TCP dump that will basically capture path MTU messages. Okay. And in the second terminal instance, we are going to run a monitor session in the Arista CEOS image, and this will basically monitor the packets that's being sent out the ETH1 interface. And the ETH1 interface is basically the interface that's connected to the control plane node. So we're going to run a TCP dump there. That's going to mirror the packets being sent out that interface. And from terminal 3, I'm going to reinitiate that curl. Okay. All right. So what you're going to see is in terminal 2, where we have the packet capture from the Arista CEOS image, you're going to see this type of message. So let me just cancel that. Cool. So you're going to see a message where it's sending a path MTU discovery message, back to the sender, and it says unreachable, need to be fragmented. And if you look at this, it's sending the packet to 10.10.10.10, which is our control node for the cluster, right? So essentially what's happening here is the control node, like the TCP handshake completes, the sender sends a client hello for the SSL handshake, and the control node is, as the server is sending the certificate, but the packet is too large. It has a length of 1612 as shown here, and the top of rack switch or router in this case is dropping the packet and sending a path MTU discovery message, back to the sender, which is the control node in this case, saying that we need to, fragment this packet, and this is my MTU 1500, right? And if you look at the control node, it has in fact received those messages. So basically, if you look at this from the Arista switch, it has received an ICMP unreachable, need to fragment, right? However, the connection is still failing, which means the control node in this case is not adjusting its maximum segment size. Like I said, there could be issues in your network where the control node or a sender, in this case, does not even receive this packet. But in our case, it is receiving the packet, but not making the necessary adjustments. And the reason for that is if you look at the Arista switch or router in this case, this is a L3 switch basically. When it's sending the message, it's using its management interface, and the control node does a reverse path forward check for this management interface, and it has a similar interface as well. So when the switch sends it a message on using this IP address, the reverse path forward fails. And as a result, it doesn't honor this packet. It drops the packet, right? So what we're going to do next in the lab is we are going to loosen up the reverse path forward check in the control node. So let me go ahead and do that. So I am going to run this command in the control node, which is going to basically change reverse path forward check to loose mode. And if I now run the curl, you can see that it was successful, right? So if I do a -vv, that curl was successful. And that's because the control node is now honoring the path MTU discovery messages being sent by the switch and adjusting the maximum segment size. So if I run another TCP dump and grep for MSS, let me do that curl one more time, we can see that the MSS in fact changed. So earlier it was 8960 and now the MSS is 1460. And as a result, that session completes. So let me exec back to the control node to reiterate the point I made about the reverse path forward check if it wasn't very clear. So if I do a show IP route get for the management IP of the Arista CEOS switch, the route points to 172.18.0.1. And that's because in this topology, there is a management network, and the Arista switch also has a leg on this management network. And the IP 172.20.20.2 is in that management range. So when the switch here or the router here, I know I tend to use it interchangeably, but this is basically a layer 3 switch. When it sends an ICMP message using that IP through ETH1, the control node is going to drop that packet because it has a route to that IP address through ETH0, right? So when it receives a packet from an interface through which it doesn't have a route, it's going to drop that packet. And that's basically the reverse path forward check. It is a security mechanism. So in this node, we changed it to loose so that it does not drop the packet and uses the packet to adjust the MSS of this TCP session, right? Now, this is not something that you would want to do in a production network. You would want to maintain the reverse path forward check as strict, but I'm just using it to demonstrate how the TCP session can adjust the maximum segment size due to these path MTU discovery messages. Now, one more interesting thing is, after a session such as this, if I do a show IP route get to 10.10.20.20, which is worker 3, in the route, you're going to see the MTU reflected as well, right? So if I change the reverse path back to strict, my connection is still going to work because the route to the worker 3 node now has an MTU reflected in the routing table. However, that once that cache expires, so it has about 286 seconds, I'm going to let it expire. You're going to see that this connection is going to fail. All right, so the cache has now expired. As you can see, if I do a IP route get to 10.10.20.20, I don't see the MTU in the route anymore. And if I go back and reinitiate that connection, you're going to see a timeout. All right, so it's something to bear in mind. All right, we got into the weeds of networking there. I hope you found it informative. I've definitely seen a few clusters impacted due to MTU issues, so it's important to bear these in mind. That's it for this video. I will see you in the next one. Thanks for watching, and bye for now.